Imagine standing on a platform, rotating at 1,670 kilometers per hour. You'd be ripped off instantly, thrown into the air like a rag doll. Yet right now, that's exactly what's happening to you. Earth beneath your feet is spinning at that incredible speed, and you're standing here calmly, completely unaware. Buildings stand tall, oceans stay in place, and the atmosphere doesn't get left behind in space. Something is holding everything down with invisible chains, something so powerful, yet so gentle that you've never even noticed it your entire life. Today, we're uncovering the cosmic force that keeps 7.8 billion people glued to a spinning rock, and why without it, we'd all vanish in an instant. If you enjoy discovering the hidden forces that shape our existence, make sure to hit that subscribe button. Let's start with something that sounds absolutely absurd. Right now, as you watch this video, you are moving. Not just moving, but racing through space at speeds that would make a jet pilot jealous. If you're sitting near the equator, the ground beneath you is rotating at approximately 1,670 kilometers per hour. That's 1,038 miles per hour for those keeping track. To put this in perspective, the speed of sound is about 1,235 kilometers per hour. You are moving faster than sound itself. But here's what makes this truly mind-boggling. You feel absolutely nothing. There's no wind rushing past your face, no sense of acceleration, no dizziness or vertigo. When you pour a glass of water, it doesn't slosh to one side. When you throw a ball straight up, it comes straight back down into your hands. Birds fly in every direction without being swept backward. Clouds drift lazily across the sky as if nothing is happening at all. Everything around you behaves as if you're standing on a completely stationary surface. This should be impossible. Think about what happens when you're in a car, traveling at just 100 kilometers per hour, and the driver slams on the brakes. You lurch forward violently. Your body wants to keep moving at that speed, while the car decelerates. Now multiply that speed by 16. Imagine what should happen if you're moving 16 times faster than a speeding car. The forces involved should be astronomical. You should be experiencing constant, overwhelming sensations of motion. Yet here we are, completely oblivious. For thousands of years, this observation led humanity to a perfectly reasonable conclusion. Earth must not be moving at all. Ancient Greek philosophers looked at the world around them and saw birds flying freely in all directions, clouds drifting peacefully, objects falling straight down. If Earth were spinning, they reasoned, surely we would feel it. Surely everything would be chaos. The fact that we didn't feel any motion seemed like irrefutable proof that Earth was stationary, the unmoving center of the universe, with the sun, moon, and stars revolving around us. This belief persisted for millennia because it matched our direct experience. Our senses told us we were standing still, and our senses had never lied to us before. Why would they start now? It wasn't until the 1600s, when scientists like Galileo Galilei and later Isaac Newton began to understand the true nature of motion and gravity, that humanity realized something profound. Our senses had been deceiving us all along. We weren't standing still. We had never been standing still. We were spinning wildly through space, and we just couldn't feel it. But why? What cosmic conspiracy keeps this motion hidden from us? The answer lies in understanding three fundamental concepts: the nature of motion itself, the invisible force that holds us down, and the perfect mathematical balance that makes our spinning planet feel like solid ground. Let's begin with motion. When you're sitting in a car, traveling down a straight highway at a constant speed, with smooth roads and no bumps, you might close your eyes and feel like you're barely moving. If the ride is smooth enough, you could balance a pencil on its tip or pour water into a glass with perfect precision. This is because your body doesn't feel motion itself. What your body feels is change in motion. We don't sense velocity, we sense acceleration. This principle is called the law of inertia, and it was one of Isaac Newton's greatest insights. An object in motion tends to stay in motion at the same speed and in the same direction unless something forces it to change. When you're moving at a constant velocity, everything in your reference frame, including your body, the air around you, and any objects with you, are all moving together at that same velocity. There's no relative motion between you and your immediate environment, so you perceive stillness. This is exactly what's happening with Earth's rotation. Our planet spins at a constant rate, completing one full rotation every 23 hours, 56 minutes, and 4.09 seconds. That's called a sidereal day, the time it takes for Earth to rotate once relative to the distant stars. This rotation has been steady for billions of years, with only tiny variations. Because the speed is constant and everything on Earth's surface, the ground, the atmosphere, the oceans, buildings, trees, and you, is rotating together at the same rate, there's no relative motion for you to feel. But wait a moment. If you've ever been on a merry-go-round or a spinning carnival ride, you know that rotation definitely feels different from straight-line motion. Even at constant rotational speed, you feel pushed outward, away from the center. Children on a spinning playground roundabout feel themselves sliding toward the edge. They have to grip tightly to stay on. This outward push is called centrifugal force, though physicists will tell you it's not really a force at all. It's the result of inertia trying to make you travel in a straight line while the rotating platform forces you to curve. So here's the critical question. If rotation creates this outward push, and Earth is rotating incredibly fast, why don't we feel ourselves being flung outward into space? Why doesn't that centrifugal effect overcome everything and send us flying? The answer is that we do experience that outward push. Right now, as you sit or stand, there is a centrifugal effect trying to throw you off Earth and into space. The rotation of our planet is actively attempting to launch you on a one-way journey to the stars. But you don't fly away for one simple reason. Something far more powerful is holding you down. Something so strong that the centrifugal force from Earth's rotation is completely overwhelmed, rendered almost insignificant. That something is gravity. Gravity is the invisible hand that keeps your feet on the ground, the mysterious force that makes objects fall, the cosmic glue that holds planets in orbit around stars and moons in orbit around planets. Every object with mass attracts every other object with mass. Earth, with its enormous mass of 5.97 times 10 to the power of 24 kilograms, pulls on every atom in your body with relentless force. This pull is what we call your weight. But here's where the magic happens. The gravitational pull keeping you on Earth's surface is far, far stronger than the centrifugal effect trying to throw you off. How much stronger? Let's do the mathematics. At the equator, where Earth's rotational speed is highest, the centrifugal acceleration is about 0.0337 meters per second squared. Now, gravity's acceleration at Earth's surface is approximately 9.8 meters per second squared. That means gravity is pulling you down with a force roughly 290 times stronger than the centrifugal effect is pushing you up. It's not even close to a fair fight. Gravity wins overwhelmingly. To put this in more tangible terms, if you weigh 70 kilograms, that's about 154 pounds. The centrifugal force from Earth's rotation reduces your weight by only about 240 grams, roughly half a pound. You're slightly lighter at the equator than you would be at the poles, where there's no rotational motion. But the difference is so small, you'd never notice it without extremely sensitive instruments. This is why we don't fly off. Gravity's grip is so powerful that Earth's rotation barely loosens it. We're held down by a force of nature so fundamental, so overwhelming, that the planet can spin at over 1,600 kilometers per hour beneath our feet, and we remain firmly planted on the surface, completely unaware of the cosmic carousel we're riding. But this raises another question, one that might have already occurred to you. If Earth is spinning so fast, what about the atmosphere? Air isn't stuck to the ground like we are. Air can flow freely. So why doesn't the atmosphere get left behind as Earth rotates? Why isn't there a constant catastrophic wind as the planet spins beneath the air? This is a brilliant question, and it troubled early scientists who first proposed that Earth rotates. The answer reveals something crucial about how fluids behave when they're in contact with rotating surfaces. When Earth began rotating billions of years ago as it formed from the primordial solar nebula, the atmosphere rotated with it from the very beginning. There was never a moment when the solid Earth started spinning beneath a stationary atmosphere. They've been partners in this dance since the planet's birth. Over billions of years, friction between Earth's surface and the air molecules in contact with it has kept the atmosphere spinning at the same rate as the planet. Air molecules at ground level are constantly colliding with the surface, trees, buildings, mountains, hills, and through these countless collisions, they exchange momentum. The surface drags the air along with it. Layer by layer, through molecular collisions, this motion propagates upward through the atmosphere. The air doesn't just sit on top of a spinning Earth like a stationary blanket. It rotates with Earth as part of a unified system. This is why, when you're in an airplane flying at 10,000 meters, you don't feel like you're flying into a stationary atmosphere while Earth spins beneath you. The air at that altitude is also rotating with the planet. Everything, from the ground to the upper reaches of the atmosphere, participates in Earth's rotation. There's no relative motion between different layers, at least not due to the basic rotation itself. Of course, there are winds and weather patterns, but these are caused by other factors like temperature differences and pressure gradients, not by the fundamental rotation of the planet. Here's a way to visualize this. Imagine a bowl filled with honey. If you slowly start rotating the bowl, at first only the honey touching the sides and bottom will move. But gradually, through the honey's viscosity, its stickiness, the motion spreads inward and upward. Eventually, all the honey in the bowl is rotating together with the bowl. The honey isn't being left behind, it's being carried along. Earth's atmosphere works the same way, though the process is mediated by friction and molecular collisions rather than viscosity in the same sense. Now, you might be thinking, okay, gravity keeps us from flying off, and the atmosphere rotates with us. But what about that 1,670 kilometers per hour figure? That sounds terrifyingly fast. How can anything structural survive moving at such speed? How do buildings stand? How do trees not snap? How does anything remain intact? This concern comes from a common confusion about what speed really means in physics. When we talk about something moving at 1,670 kilometers per hour, we're describing its velocity relative to some reference point. Speed is always relative. There's no such thing as absolute speed in the universe, only speed compared to something else. When you're sitting in your home right now, you're indeed moving at over 1,000 kilometers per hour relative to Earth's axis. But relative to your house, your furniture, the ground beneath you, you're moving at 0 kilometers per hour. You're stationary in your own reference frame. This is the key insight. The stress that structures experience doesn't come from their absolute velocity through space, but from forces acting on them and from differential motion, parts of the structure moving at different speeds relative to each other. A building doesn't care that it's spinning with Earth at enormous speed, because every brick, every beam, every foundation stone is spinning together at the same rate. There's no internal stress from the rotation itself, because there's no relative motion between the building's components. It's exactly like how passengers in a smoothly cruising airplane don't feel the plane's 600 kilometer per hour velocity. Everyone and everything in the plane is moving together. The only time you'd have a problem is if different parts of Earth's surface were rotating at significantly different speeds, creating what's called differential rotation. Then structures spanning those regions would experience twisting forces. But Earth rotates as a relatively solid body. Yes, there are tiny variations. The equator bulges slightly due to centrifugal force, and there are complex motions in Earth's molten outer core. But the crust, where we live, spins as essentially a single unit. Every point at a given latitude rotates at the same speed. So, the incredible velocity of Earth's rotation doesn't threaten structures, because velocity alone doesn't cause stress. What causes stress is acceleration, changes in velocity, or differential motion. As long as everything moves together smoothly, the speed itself is irrelevant. But let's push this understanding further. We've established that Earth's rotation is steady, that gravity keeps us down, and that the atmosphere moves with us. But there's still something fascinating to explore. How does Earth's rotation speed vary, depending on where you are on the planet? That 1,670 kilometers per hour figure applies specifically at the equator. What about everywhere else? This is where geometry comes into play. Earth is roughly spherical. More precisely, it's an oblate spheroid, slightly flattened at the poles and bulging at the equator. When Earth completes one rotation, every point on the surface must complete one full circle around Earth's axis in the same 24-hour period. But the size of those circles varies dramatically depending on your latitude. At the equator, you're at Earth's maximum radius from the axis of rotation, about 6,378 kilometers. 2. Complete a circle at that radius in 24 hours requires moving at about 1,670 kilometers per hour. But as you move toward the poles, your distance from Earth's axis decreases. The circle you need to complete gets smaller. Therefore, the speed required to complete that circle in 24 hours also decreases. By the time you reach latitude 45 degrees, north or south, roughly the latitude of cities like Turin in Italy or Minneapolis in the United States, your rotational speed has dropped to about 1,180 kilometers per hour. At 60 degrees latitude, the approximate latitude of Oslo, Norway, or Anchorage, Alaska, you're moving at about 835 kilometers per hour. And at the poles themselves, you're simply rotating in place. Your rotational velocity is zero. This variation in speed has practical consequences. For example, it affects rocket launches. When you launch a rocket eastward from near the equator, you get a free boost from Earth's rotation. The rocket is already moving at over 1,600 kilometers per hour before its engines even fire. That's why many spaceports are located near the equator, places like the European Space Agency's launch site in French Guiana, or NASA's Kennedy Space Center in Florida, relatively low latitude. They take advantage of this natural velocity boost. The variation in rotational speed also influences weather patterns. The Coriolis effect, which causes hurricanes to spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, arises directly from differences in rotational speed at different latitudes. As air masses move north or south, they're moving between regions with different eastward velocities, and this creates the apparent deflection we observe as the Coriolis effect. But I'm getting ahead of myself. We'll explore these consequences in more detail shortly. For now, the key point is this: Earth's rotation speed is not uniform across the planet's surface. It's fastest at the equator and decreases to zero at the poles. This might seem like it would create problems, wind shear, structural stress, or other complications. But remember, at any given latitude, all points at that latitude are moving together at the same speed. There's no relative motion between points at the same latitude, so there's no direct conflict or friction between different parts of the planet's surface due to the rotation itself. Now let's explore something truly fascinating: what Earth's rotation actually does to our daily lives, often in ways so subtle we never notice. The spinning of our planet isn't just a curious fact. It shapes weather patterns, affects navigation, influences ocean currents, and even changes the very shape of the planet itself. Understanding these effects reveals just how deeply connected we are to this cosmic motion we cannot feel. Let's start with one of the most important consequences: the Coriolis effect. This is the phenomenon responsible for the characteristic spiral shape of hurricanes, the circulation patterns of ocean currents, and even the direction water drains in certain circumstances, though that last one is more complicated than popular myths suggest. The Coriolis effect arises because different latitudes on Earth move at different speeds, as we discussed earlier. Imagine you're standing at the equator and you throw a ball directly north towards someone standing far away at a higher latitude. From your perspective, you threw the ball straight. But here's what happens. As the ball travels north, it's moving over ground that's rotating slower than the ground you threw it from. The ball retains the eastward velocity it had when it left your hand at the equator, about 1,670 kilometers per hour. But the ground it's traveling over is moving slower eastward. The result? The ball appears to curve to the right, toward the east, from the perspective of someone watching from the ground. This isn't because any force is pushing the ball sideways. The ball is traveling in a straight line through space. But because the ground beneath it is rotating at different speeds at different latitudes, observers on that rotating ground see the ball's path as curved. This apparent deflection is the Coriolis effect, named after the French mathematician Gaspard Gustave de Coriolis, who described it in 1835. The Coriolis effect is incredibly weak for small-scale motions. It won't significantly deflect a baseball or affect which direction water swirls down your drain, despite what you might have heard. Those small-scale flows are dominated by other factors like the shape of the basin and existing water currents. But for large-scale motions, air masses moving thousands of kilometers, ocean currents flowing across entire oceans, the Coriolis effect becomes dominant. This is why hurricanes spin. When air rushes toward a low-pressure center, it doesn't flow straight in. The Coriolis effect deflects it, causing it to spiral. In the northern hemisphere, the deflection is to the right, creating counterclockwise rotation. In the southern hemisphere, the deflection is to the left, creating clockwise rotation. At the equator itself, where the Coriolis effect is zero because you're not moving between different latitudes, hurricanes cannot form. There's a narrow band around the equator, roughly between 5 degrees north and 5 degrees south latitude, where tropical cyclones simply don't develop. Earth's rotation creates a hurricane-free zone right at its fastest spinning point. Ocean currents also dance to the rhythm of Earth's rotation. The great circular current systems called gyres, like the North Atlantic gyre or the South Pacific gyre, rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere because of the Coriolis effect. These massive rivers of water, stretching across entire ocean basins, are guided by the same rotational physics that shapes hurricanes. The Gulf Stream, which carries warm water from the tropics to the North Atlantic and moderates Europe's climate, follows its path partly because of Earth's rotation. Even the flight paths of long-distance aircraft must account for the Coriolis effect. A plane flying from New York to London cannot simply point itself northeast and fly straight. The rotation of Earth beneath it means it must constantly adjust its heading to compensate for the Coriolis deflection. Navigation systems in modern aircraft automatically account for this, but in the early days of aviation, pilots had to manually calculate these corrections. Earth's rotation, invisible to our senses, demanded respect from aviators. But the Coriolis effect is just one consequence of Earth's rotation. Another profound effect is the planet's shape itself. Earth is not a perfect sphere. It's an oblate spheroid, slightly flattened at the poles and bulging at the equator. The difference is subtle, but measurable. Earth's equatorial diameter is about 43 kilometers larger than its polar diameter. That's a difference of about 0.33%, small but significant. Why this bulge? Centrifugal force. Remember, the centrifugal effect from Earth's rotation tries to throw everything outward, away from the axis. At the equator, where rotational speed is highest, this outward push is strongest. Over billions of years, this force has caused Earth's malleable interior to redistribute, flowing outward at the equator and inward at the poles, until it reached a stable equilibrium shape. The planet literally reshaped itself in response to its own rotation. This equatorial bulge has consequences. For one, it means that the point on Earth's surface farthest from the planet's center isn't Mount Everest, despite Everest being the highest mountain above sea level. The farthest point is actually the summit of Mount Chimborazo in Ecuador. Chimborazo sits almost exactly on the equator, where Earth's radius is greatest. Even though Chimborazo's peak is only 6,263 meters above sea level, compared to Everest's 8,849 meters, Chimborazo's location on the equatorial bulge places its summit about 2,150 meters farther from Earth's center than Everest's summit. If you wanted to stand at the point on Earth's surface most distant from the planet's core, you'd climb Chimborazo, not Everest. The equatorial bulge also affects gravity. Because the equator is farther from Earth's center, and because centrifugal force reduces the effective gravitational pull there, objects weigh slightly less at the equator than at the poles. A person weighing exactly 70 kilograms at the North Pole would weigh about 69.65 kilograms at the equator, a difference of about 350 grams. This variation is why precision, measurements, especially in science and metrology, must account for location. The standard definition of the kilogram, before it was redefined in terms of fundamental constants in 2019, had to specify the gravitational conditions under which it was measured. Now, let's conduct a thought experiment, one that will truly reveal just how essential Earth's rotation is to our existence. Imagine, for a moment, that Earth suddenly stopped spinning, not gradually slowing down over millions of years, but stopping instantly, frozen in place, while everything on its surface continued moving at its original rotational velocity. What would happen? The results would be absolutely catastrophic, apocalyptic beyond imagination. Remember, at the equator, everything is moving eastward at 1,670 kilometers per hour. If the ground suddenly stopped but you kept moving, you'd be instantly launched eastward at that speed. Buildings, trees, cars, oceans, everything not firmly attached to the bedrock would be hurled eastward like projectiles from an incomprehensibly powerful cannon. The atmosphere, all 5 quadrillion tons of it, would become a supersonic wind of unimaginable violence, scouring the surface clean. Oceans would surge eastward in mega tsunamis thousands of meters high, washing over continents with the force of millions of nuclear weapons. Mountains would be uprooted. The very landscape would be obliterated. The kinetic energy that would need to be dissipated is equivalent to billions of nuclear arsenals exploding simultaneously. But it gets worse. Earth's rotation is intimately connected to its magnetic field. Our planet's magnetic field, which protects us from deadly solar radiation and cosmic rays, is generated by the motion of liquid iron in Earth's outer core. This motion, driven by convection and Earth's rotation, creates electrical currents that produce the magnetic field through a process called the geodynamo. If Earth stopped rotating, this mechanism would be disrupted. The magnetic field would weaken and potentially collapse. Without the magnetic field's protection, solar wind, charged particles streaming from the sun, would directly strike Earth's atmosphere. Over time, the atmosphere itself would be stripped away, blown into space by the relentless solar wind, just as happened to Mars billions of years ago after that planet lost its magnetic field. Earth would become a dead, airless rock, its oceans evaporated, its surface scorched by radiation. Even if we imagine a gentler scenario where Earth gradually slowed down over thousands or millions of years, the consequences would still be dire. Days would become longer and longer. If Earth rotated just half as fast as it does now, each day would last 48 hours. 24 hours of scorching sunlight, followed by 24 hours of freezing darkness. Temperature extremes would become far more severe. Deserts would expand. Weather patterns would transform completely. The delicate balance that makes Earth habitable would shatter. Fortunately, there's no realistic mechanism that could stop Earth's rotation. The planet's angular momentum, its rotational inertia, is stupendously large. To stop Earth from spinning would require applying an opposing torque so immense that nothing in the solar system short of a planetary collision could provide it. Even the most powerful earthquakes barely affect Earth's rotation rate, changing the length of a day by microseconds at most. The devastating earthquake that struck Japan in 2011, one of the most powerful ever recorded, shortened Earth's day by about 1.8 microseconds. You'd need billions of such earthquakes happening simultaneously to measurably slow Earth's rotation. There is, however, a natural process that is gradually slowing Earth's rotation: tidal friction. The moon's gravity pulls on Earth's oceans, creating the tides we observe twice daily as the planet rotates beneath these tidal bulges. But here's the key detail. Earth's rotation is slightly faster than the moon's orbit. As Earth spins, it tries to drag the tidal bulges ahead of the moon. The moon's gravity pulls back on these bulges, creating a braking force, a torque that gradually slows Earth's rotation. This process is incredibly slow. Earth's day is lengthening by about 1.7 milliseconds per century. That might not sound like much, but over hundreds of millions of years, it adds up. Fossil evidence from ancient corals and other organisms that grew in daily and yearly cycles reveals that 400 million years ago, a year contained about 410 days. Each day was only about 21.5 hours long. Earth was spinning noticeably faster. As Earth's rotation slows due to tidal friction, angular momentum must be conserved. That momentum is transferred to the moon, which gradually moves farther from Earth. The moon is currently receding at a rate of about 3.8 centimeters per year. Billions of years in the future, this process will continue until Earth and the moon become tidally locked, just as the moon is already tidally locked to Earth, always showing us the same face. When that happens, Earth's day will equal the moon's orbital period, both lasting about 47 current days. One side of Earth would permanently face the moon, the other side would never see it. But don't worry about this. The process will take billions of years, far longer than the time remaining before the sun expands into a red giant and engulfs the inner planets. Earth's rotation, while not eternal, will outlast our sun's lifetime on the main sequence. Let's return to the present and consider another subtle but important consequence of Earth's rotation: its effect on the planet's climate and habitability. The rotation rate of a planet profoundly influences its climate patterns. Earth's 24-hour day creates a rhythm of heating and cooling that's relatively gentle. The daytime side has time to warm up, but not to extremes. And the nighttime side cools down, but not catastrophically. Compare this to a planet with very slow rotation. Venus, for example, rotates once every 243 Earth days. Its day is longer than its year. This means Venus's day side faces the sun for months at a time, while the night side is plunged into equally long darkness. Combined with Venus's thick atmosphere and runaway greenhouse effect, this creates a hellish world where temperatures exceed 470 degrees Celsius. The slow rotation contributes to the planet's extreme climate. On the other hand, planets that rotate extremely fast can have their own problems. Jupiter, the solar system's largest planet, rotates once every 10 hours despite being 11 times wider than Earth. This rapid rotation creates powerful weather systems, including the Great Red Spot, a storm larger than Earth that has raged for centuries. Jupiter's fast rotation stretches it into a distinctly oblate shape, much more pronounced than Earth's subtle bulge. Earth's rotation rate seems to fall in a sweet spot, fast enough to create moderate temperature swings and distribute heat relatively evenly, but slow enough to avoid the kind of violent weather systems that would make life difficult. This is partly coincidence and partly a result of the specific conditions under which Earth formed. The impact that created our unusually large moon, an event called the giant impact or Big Whack, also likely influenced Earth's rotation rate. We're fortunate that the outcome was favorable. Speaking of the moon, let's appreciate its role in stabilizing Earth's rotation. The moon's gravitational influence doesn't just create tides and slowly break Earth's rotation. It also stabilizes Earth's axial tilt, the angle at which our rotation axis is tilted relative to our orbital plane around the Sun. Earth's axis is currently tilted at about 23.44 degrees, and this tilt gives us our seasons as different hemispheres lean toward or away from the Sun during the year. Without the moon, Earth's axial tilt would vary chaotically over millions of years due to gravitational perturbations from other planets, especially Jupiter. Computer simulations show that a moonless Earth could see its axis tilt anywhere from 0 to 85 degrees over timescales of millions of years. Imagine the climate chaos that would result. Regions that are temperate 1 million years could become polar deserts the next, then tropical jungles, then polar again. Complex life would struggle to adapt to such wild swings. The moon's presence damps these oscillations, keeping Earth's tilt relatively stable, varying only between about 22 and 24.5 degrees over a 41,000-year cycle. This stability has been crucial for the development of complex life on Earth. The moon, born from a catastrophic collision that could have sterilized our world, became the guardian of our planet's climate stability. Earth's rotation and the moon's orbit are partners in creating the conditions that make our world habitable. Now let's examine something you might have wondered about. If Earth is spinning and we're moving with it, what happens when we jump? When you leap into the air, you're momentarily not in contact with the ground. Does Earth continue spinning beneath you while you're airborne, so you land in a slightly different spot? The answer is no. You land in the same spot, and here's why. When you jump, you don't leave Earth's motion behind. You carry that eastward velocity with you. Remember, you're not just spinning with Earth. You're moving through space with the planet, orbiting the Sun at about 107,000 kilometers per hour, and moving with the solar system around the galaxy at about 720,000 kilometers per hour. None of these motions suddenly stop when your feet leave the ground. When you jump straight up, you're actually following a very slight parabolic arc through space, not just moving straight up and down. But because the ground beneath you is moving with you at the same velocity from your perspective and from the perspective of anyone standing nearby, you go straight up and come straight down. The eastward motion you had when you jumped is conserved while you're in the air, so you maintain your position relative to the rotating surface. This is identical to what happens inside an airplane. If you toss a ball straight up while the plane is cruising at 600 kilometers per hour, the ball doesn't suddenly fly backward and smash into the rear of the cabin. The ball, you, and the air inside the cabin are all moving forward at 600 kilometers per hour together. When you toss the ball up, it retains that forward motion. From your perspective inside the plane, it goes straight up and comes straight down into your hands. Earth is like that airplane cabin, but on a vastly larger scale. The air, the ground, the buildings, and everything else are all part of one cohesive system moving together. When you jump, you remain part of that system. You don't somehow separate from Earth's motion just because you're not touching the surface. However, there are extremely subtle effects if you want to get technical. When you jump, you're momentarily at a slightly higher altitude where the air is rotating at a very slightly different speed due to conservation of angular momentum. Objects farther from Earth's center move through larger circles in the same time period, so they have slightly higher tangential velocity. This effect is utterly negligible for a jump of a meter or two. We're talking about differences measured in millimeters over a multi-second flight, but for high-altitude projectiles, like long-range artillery shells or rockets, these effects must be calculated and corrected for. Snipers taking extremely long-distance shots, beyond 1,000 meters, must account for the Coriolis effect. A bullet traveling for several seconds over a long distance will drift slightly due to Earth's rotation. In the northern hemisphere, a bullet fired north will drift to the right, east. A bullet fired south will also drift right, which is westward. The effect is small, perhaps a few centimeters over 1,000 meters, but for precision shooting, that's the difference between a hit and a miss. Artillery crews have long tables and calculations to account for Earth's rotation when aiming their guns. During World War I, when long-range artillery became common, gunners had to learn to include Coriolis corrections in their firing solutions. A shell fired at a target 20 kilometers away would miss by dozens of meters if Earth's rotation wasn't accounted for. The planet's spin, imperceptible to our senses, became a critical factor in the mathematics of war. Let's explore one more fascinating consequence of Earth's rotation: the Foucault pendulum. In 1851, French physicist Léon Foucault demonstrated Earth's rotation in a dramatic and visible way by suspending a 67-meter pendulum from the dome of the Pantheon in Paris. The pendulum was free to swing in any direction, and Foucault set it swinging along one particular plane. Here's the remarkable thing. Over the course of hours, the plane of the pendulum's swing appeared to rotate. The pendulum itself continued swinging along the same plane in space, but because Earth was rotating beneath it, from the perspective of observers standing on the rotating floor, the pendulum's swing seemed to turn. In Paris, at about 49 degrees north latitude, the pendulum's plane rotates fully once every 32 hours. At the North or South Pole, a Foucault pendulum would complete a full rotation in exactly 24 hours, one full rotation of Earth. At the equator, the pendulum's plane wouldn't rotate at all. The rate of rotation depends on your latitude, specifically on the sign of your latitude. This elegant device provided visual, undeniable proof of Earth's rotation to anyone who watched it, a slow-motion revelation of the planet's spin. Foucault pendulums are now found in museums and science centers around the world, mesmerizing visitors with their slow, stately rotation. They serve as a reminder that we live on a spinning world, even though we cannot feel it. Earth's motion, hidden from our immediate senses, can be revealed through careful observation and clever experiments. The rotation of Earth also plays a crucial role in navigation. For thousands of years, sailors used the apparent motion of the stars across the sky to determine their latitude. The North Star, Polaris, sits almost exactly above Earth's North Pole, so the angle of Polaris above the horizon equals your latitude in the Northern Hemisphere. This only works because Earth rotates around a fixed axis, pointing toward Polaris. If Earth didn't rotate, or if its axis wandered chaotically, celestial navigation would be impossible. The invention of accurate clocks in the 18th century, particularly John Harrison's marine chronometers, allowed sailors to determine longitude by comparing local solar time with the time at a reference meridian like Greenwich. This, too, depends on Earth's steady rotation. The planet completes 360 degrees of rotation in 24 hours, which equals 15 degrees per hour. If you know the time difference between your location and Greenwich, you can calculate how many degrees of longitude you've traveled east or west. Every hour of time difference equals 15 degrees of longitude. Modern GPS systems also depend on accounting for Earth's rotation. GPS satellites orbit at about 20,000 kilometers altitude, circling Earth twice per day. The satellites transmit signals encoded with precise timestamps from atomic clocks. Your GPS receiver compares these timestamps with its own clock to calculate how far away each satellite is based on the light travel time of the signals. By triangulating distances to multiple satellites, the receiver determines your position. But here's the catch. The satellites are moving, and Earth is rotating beneath them. The GPS system must account for both the satellite's orbital motion and Earth's rotation to provide accurate positions. Additionally, because the satellites are moving at high speeds and experiencing weaker gravity than objects on Earth's surface, they experience time dilation effects from both special and general relativity. Their clocks run at different rates than clocks on the ground. These relativistic effects, just tens of microseconds per day, would accumulate into positioning errors of kilometers if not corrected. Earth's rotation, relativity, and satellite motion all dance together in the intricate choreography that makes GPS work. So far, we've focused on Earth's rotation, its daily spin on its axis. But Earth's rotation is only one of several motions we're experiencing right now. We're not just spinning, we're also orbiting the Sun. The Sun is orbiting the center of our galaxy, and our galaxy itself is moving through the universe. Each of these motions happens at speeds that dwarf even Earth's impressive rotational velocity, yet we feel none of it. Understanding why requires us to zoom out and see the bigger cosmic picture. Let's start with Earth's orbit around the Sun. Our planet traces an elliptical path around our star, completing one full orbit every 365.256 days. That's why we need leap years, to account for that extra quarter day. The distance Earth travels in one orbit is enormous, about 940 million kilometers. To cover that distance in 1 year, Earth must move at an average speed of about 107,000 kilometers per hour, or about 29.8 kilometers per second. Think about that for a moment. Right now, you're not just spinning at over 1,600 kilometers per hour due to Earth's rotation. You're also hurtling through space at over 100,000 kilometers per hour as Earth orbits the Sun. That's roughly 90 times faster than a jetliner. At this speed, you could travel from New York to London in about 5 seconds, yet you feel absolutely nothing. Why? For the same reason you don't feel Earth's rotation. The motion is smooth and constant. Earth's orbital path is very nearly circular. The orbit is only slightly elliptical, and our planet maintains a steady velocity along that path. There's no sudden acceleration, no jarring changes in direction. Everything on Earth, the atmosphere, the oceans, every atom in your body moves together through space at this orbital velocity. From our perspective, riding along with Earth, we're stationary in our own reference frame. But wait a moment. Earth's orbit is curved. We're constantly changing direction as we circle the sun. Doesn't changing direction mean we're accelerating? Yes, it does. Whenever you change direction, even if your speed remains constant, you're experiencing acceleration. A car turning a corner at constant speed is accelerating toward the center of the turn. Similarly, Earth is constantly accelerating toward the sun as it orbits. This acceleration is called centripetal acceleration, the inward acceleration that keeps an object moving in a circular path. For Earth's orbit, this centripetal acceleration is about 0.006 meters per second squared, directed toward the sun. Now compare that to gravity's acceleration at Earth's surface, 9.8 meters per second squared. The orbital acceleration is about 1/1600th as strong as the gravitational pull keeping you on Earth's surface. Moreover, this orbital acceleration affects everything on Earth equally. The entire planet and everything on it is falling toward the sun together. This is the essence of orbit, constantly falling toward a massive object, but also moving sideways fast enough that you keep missing it. Because everything is in free fall together, we don't experience the acceleration as a force. It's identical to the weightlessness astronauts experience in orbit around Earth. They're not beyond Earth's gravity. They're in free fall. And because their spacecraft and everything inside it is falling together, they float weightlessly. We're in free fall around the sun, but because we're doing it together with our entire planet, we don't perceive it. The ground pushes up on us with enough force to counteract Earth's gravity, but not to counteract our orbital acceleration, because that acceleration is already shared by the ground itself. From our perspective, standing on Earth's surface, we're simply stationary. The sun's gravity, pulling everything toward it at the same rate, becomes invisible to our senses. This is one of the profound insights of Einstein's general theory of relativity. Gravity and acceleration are equivalent. An astronaut in orbit experiences weightlessness not because gravity has disappeared, but because they're in free fall. Similarly, we don't feel Earth's orbital acceleration around the sun because we're all falling together. Gravity shapes the path we follow through space, but from our perspective, we're simply moving in a straight line through curved space-time. Now let's zoom out even further. Earth orbits the sun, but the sun isn't stationary. Our entire solar system is orbiting the center of the Milky Way galaxy. The sun, along with all its planets, moons, asteroids, and comets, traces a vast circular path around the galactic core, which lies about 26,000 light-years away in the direction of the constellation Sagittarius. The speed required to complete this galactic orbit is staggering. Our solar system moves at approximately 230 kilometers per second, or about 828,000 kilometers per hour, relative to the galactic center. That's roughly 770 times faster than Earth's orbital speed around the sun. At this velocity, you could travel from Earth to the Moon in about 28 minutes. Yet once again, we feel nothing. The galactic orbit is so vast and the motion so smooth that there's no detectable acceleration from our perspective. The solar system takes about 230 million years to complete one orbit around the galaxy. That's called a galactic year or cosmic year. Since Earth formed about 4.5 billion years ago, our planet has completed roughly 20 orbits around the galactic center. Every living thing on Earth is on its 20th lap around the Milky Way, but the motion doesn't stop there. The Milky Way itself is moving through space. Our galaxy, along with its neighbor Andromeda and several dozen smaller galaxies, forms a structure called the local group. The local group, in turn, is part of a larger structure called the Virgo supercluster, a vast collection of galaxy clusters spanning over 100 million light years. All these structures are in motion, influenced by the gravitational pull of surrounding matter and the expansion of the universe itself. Relative to the cosmic microwave background radiation, the afterglow of the Big Bang that fills all space, our local group is moving at about 630 kilometers per second, or roughly 2.27 million kilometers per hour. This motion is called our peculiar velocity, the velocity we have relative to the overall expansion of the universe. We're being pulled in the direction of a concentration of mass called the Great Attractor, a gravitational anomaly located roughly 250 million light years away. So let's add it all up. You are simultaneously spinning with Earth at up to 1,670 kilometers per hour, orbiting the Sun at 107,000 kilometers per hour, circling the galactic center at 828,000 kilometers per hour, and moving with the local group at over 2 million kilometers per hour. The total motion is almost incomprehensibly fast. Yet you sit or stand perfectly still from your own perspective, feeling none of it. This is the cosmic miracle of relative motion and inertia. Velocity is relative. There's no such thing as being absolutely at rest or absolutely in motion. You can only be at rest or in motion relative to some other object or reference frame. In your own reference frame, you are always at rest. The motions of Earth, the solar system, and the galaxy only become apparent when you compare your position to distant objects, stars, galaxies, or the cosmic microwave background. And because all these motions are smooth and constant, or in the case of orbital accelerations, shared equally by everything around us, there's nothing for our senses to detect. We evolved to detect changes in motion, sudden accelerations, jerks, and jolts that might indicate danger. But we have no sensory apparatus to detect constant velocity, no matter how fast. Our nervous system simply isn't wired to perceive it. This reveals something beautiful about the universe. Despite the violent speeds at which everything moves, the cosmos is arranged in nested layers of smooth, stable motion. Earth spins smoothly on its axis. Earth orbits smoothly around the Sun. The Sun orbits smoothly around the galaxy. Each motion happens at its own timescale. Each is nearly imperceptible from the perspective of the smaller scale beneath it. We live in a universe of motion, within motion, yet we can perceive it as stillness. Let's consider what would happen if any of these motions suddenly changed. Imagine if Earth's orbit around the Sun were disrupted. If our planet suddenly stopped orbiting and began falling straight toward the Sun, we would notice immediately. The sensation of changing direction would be unmistakable. We'd feel ourselves being pulled in a new direction toward the Sun. Within weeks, Earth would plunge into the Sun's outer layers, vaporizing in temperatures of millions of degrees. Or imagine if the sun suddenly stopped in its galactic orbit. The solar system would begin falling toward the galactic center, accelerating inward. The acceleration would be tiny at first. The galactic center is so far away, and its gravitational influence so gentle at this distance. But over millions of years, the solar system would spiral inward, eventually plunging into the dense star fields of the galactic core. The night sky would gradually fill with more and more stars as we fell inward, a slow-motion cosmic catastrophe. Fortunately, nothing can just suddenly stop these motions. They're governed by conservation of angular momentum, one of the most fundamental principles in physics. An object in orbital motion retains that motion unless acted upon by an external force. For Earth to stop orbiting the Sun, some massive force would have to remove all our orbital velocity, requiring energy equivalent to thousands of years of sunlight. For the Sun to stop orbiting the galactic center, forces millions of times greater still would be needed. These motions are essentially permanent on human timescales, and even on geological timescales. They're as reliable as the laws of physics themselves. Let's talk about something that might have occurred to you. If we're moving so fast through space, what about the speed of light? Einstein's special theory of relativity tells us that nothing can move faster than light, which travels at about 299,792 kilometers per second in vacuum, or roughly 1.08 billion kilometers per hour. That's the universe's ultimate speed limit. Given all the motions we've discussed, are we in danger of approaching that limit? Not even remotely close. Let's add up all our velocities in the most extreme case. Earth's rotational speed at the equator is about 0.46 kilometers per second. Earth's orbital speed around the Sun is about 29.8 kilometers per second. The Sun's orbital speed around the galaxy is about 230 kilometers per second. Our peculiar velocity with the local group is about 630 kilometers per second. If we imagine all these motions aligned in the same direction, which they're not, the total would be about 890 kilometers per second. That sounds like a lot, but it's only about 0.3% of the speed of light. We're moving at roughly 1/300th of light speed. The universe's speed limit is so far above our cosmic wanderings that we're barely creeping along in comparison. Light could lap us 300 times before we completed one circuit. We're not racing through space. We're drifting slowly and gracefully through the cosmic sea. This is fortunate because strange things happen as you approach light speed. Special relativity predicts that objects moving near light speed experience time dilation, where time passes more slowly for them relative to stationary observers, and length contraction, where objects appear compressed in their direction of motion. These effects only become significant above about 10% of light speed. At our sedate velocities, relativistic effects are utterly negligible. Time passes at the same rate for us as it would for a hypothetical observer at rest relative to the cosmic microwave background. Now let's consider how all these motions interact with each other. When Earth orbits the Sun, different sides of the planet are moving either in the same direction as the Sun's galactic orbit or opposite to it. If you're standing on the side of Earth that's moving in the same direction as the Sun's galactic motion, your total velocity through the galaxy is slightly higher than the Sun's. 6 months later, when Earth has moved to the opposite side of its orbit, you're on the side moving against the Sun's galactic motion, and your velocity is slightly lower. This creates an oscillation in your galactic velocity over the course of a year. The amplitude of this oscillation is just Earth's orbital speed, about 30 kilometers per second. So your velocity relative to the galactic center varies by plus or minus 30 kilometers per second, depending on the time of year. In January, when Earth's orbital motion is aligned with the Sun's galactic motion, you're moving about 30 kilometers per second faster through the galaxy than in July, when the motions are opposed. Does this affect anything? Not really. Not in any way we can perceive. The effect is far too small. But it does have one interesting consequence. It creates a subtle annual variation in the direction and intensity of the cosmic microwave background radiation. This radiation fills the universe uniformly, but because we're moving through it, we see it slightly blue-shifted, compressed to shorter wavelengths in the direction we're moving, and slightly red-shifted, stretched to longer wavelengths in the opposite direction. This is called the dipole anisotropy of the cosmic microwave background. As Earth orbits the Sun, the direction of our motion through the cosmic microwave background changes slightly, creating a tiny annual oscillation in the observed dipole anisotropy. This effect is measurable with sensitive instruments, and it confirms both Earth's orbital motion and the Sun's motion through the galaxy. Our cosmic motions leave subtle fingerprints in the ancient light from the Big Bang. Let's also discuss how all these motions affect our measurement of the universe. When astronomers observe distant galaxies, they must account for Earth's rotation, Earth's orbit around the Sun's orbit around the galaxy, and our local group's peculiar velocity to determine the galaxy's true motion relative to the overall expansion of the universe. This is a complex calculation involving multiple reference frames, but modern astronomy has mastered it. For example, when measuring the Doppler shift of light from a distant galaxy to determine how fast it's moving away from us due to cosmic expansion, astronomers must first subtract our own motion toward or away from that galaxy. If we happen to be on the side of Earth's orbit moving toward the galaxy, we see a slightly larger redshift than we would 6 months later when we're moving away from it. Over the course of a year, observations of the same galaxy show a periodic variation in its apparent velocity. By carefully tracking these variations, astronomers can separate our local motions from the galaxy's cosmological recession velocity. This is similar to how police radar guns work. A radar gun measures the Doppler shift of radio waves bouncing off a moving car. But if the police car itself is moving, that motion must be factored in. The radar gun measures the relative velocity between the two vehicles. Similarly, astronomical observations measure relative velocities, and careful analysis is needed to extract the absolute cosmic velocities we're interested in. There's a philosophical dimension to all this as well. The ancient Greeks and medieval scholars believed Earth was the unmoving center of the universe because that's what their senses told them. The apparent motion of the sun, moon, and stars across the sky was interpreted as evidence that these objects were orbiting a stationary Earth. It took centuries of careful observation, mathematical modeling, and intellectual courage to overturn this geocentric worldview and recognize that Earth is in motion. Nicholas Copernicus, in the 16th century, proposed a heliocentric model with Earth and the other planets orbiting the Sun. But even Copernicus believed the Sun was the fixed center of the universe. It wasn't until much later that astronomers realize the sun itself is moving, orbiting within a vast galaxy of stars. And only in the 20th century did we discover that our galaxy is just one of billions, all moving through an expanding universe with no center and no edge. Each step in this journey required scientists to look past the evidence of their senses and trust in the mathematics and observations that revealed a reality far stranger than immediate perception suggested. The fact that we don't feel Earth's rotation or any of our other cosmic motions isn't evidence that they're not happening. It's evidence that our intuition about motion, shaped by everyday experiences at human scales, fails utterly when applied to planetary and cosmic scales. This is a recurring theme in physics. Our intuition is a terrible guide to reality at scales far removed from everyday life. At quantum scales, particles behave in ways that seem impossible, existing in multiple states simultaneously, tunneling through barriers, becoming entangled across vast distances. At cosmic scales, space itself expands, time dilates, and black holes warp reality beyond recognition. And at the ordinary scales of rotating planets, we discover that we're racing through space at incomprehensible speeds while feeling nothing at all. Yet there's something deeply satisfying about understanding these hidden truths. Yes, we're spinning at over 1,600 kilometers per hour, orbiting at over 100,000 kilometers per hour, and moving through the galaxy at close to 1,000,000 kilometers per hour. But we're also safe, held securely by gravity's gentle but unbreakable grip, moving smoothly along paths carved out billions of years ago by the gravitational dance of matter and energy. We're part of a cosmic choreography so vast and so ancient that our entire civilization, from its first beginnings to its ultimate end, is but a fleeting moment in the endless turning of the celestial wheels. Understanding why we don't feel these motions connects us to fundamental principles of physics: Newton's laws of motion, Einstein's relativity, the conservation of angular momentum, the equivalence of gravity and acceleration. These aren't just abstract concepts in textbooks. They're the invisible rules governing every moment of our existence, the reasons we can walk, jump, pour water, and go about our daily lives on a planet hurtling through space. Let's consider one more aspect of Earth's motion: its axial precession. We've talked about Earth's daily rotation and how it creates day and night. But Earth's rotation axis itself is slowly wobbling, tracing out a circle in the sky over a period of about 26,000 years. This wobble, called precession, is caused by the gravitational pull of the Sun and Moon on Earth's equatorial bulge. Imagine a spinning top. When it spins upright, its axis points straight up. But as it slows down, the axis begins to wobble, tracing out a cone. The axis is precessing. Earth's rotation axis precesses in the same way, though much more slowly, and for different reasons. The axis isn't slowing down significantly, but the gravitational tugs from the Sun and Moon create a torque that makes it wobble. Currently, Earth's north pole points toward Polaris, the North Star. But 13,000 years from now, due to precession, the North Pole will point toward a different star, Vega. Another 13,000 years after that, it will point back toward Polaris. The entire cycle takes about 26,000 years. This means the constellations visible in the night sky at different seasons slowly shift over millennia. The ancient Egyptians saw different stars in their night sky than we do, and our distant descendants will see different stars still. Does this precession affect us in our daily lives? Not directly. The wobble is far too slow to perceive, but it does affect long-term climate patterns. The precession changes when Earth's perihelion, the point in its orbit closest to the Sun, occurs relative to the seasons. Currently, perihelion happens in early January, during Northern Hemisphere winter. In about 13,000 years, perihelion will occur during Northern Hemisphere summer, making those summers slightly warmer and winters slightly colder. These variations in Earth's orbit and axial tilt, including precession, are part of what are called Milankovitch cycles, named after Serbian scientist Milutin Milankovic, who studied them extensively. These cycles influence the distribution of solar energy across Earth's surface and are thought to play a role in triggering ice ages and interglacial periods. The ice ages that covered much of North America and Europe in glaciers tens of thousands of years ago were influenced by these orbital variations. So Earth's rotation, its orbit, and even the wobble of its axis all play roles in shaping our planet's climate over thousands and millions of years. The motions we cannot feel have profound consequences that ripple through geological time, sculpting continents with ice, raising and lowering sea levels, and influencing the evolution of life itself. Now let's bring all these concepts together and appreciate the remarkable perfection of the system we inhabit. Earth's rotation, its orbit, the Sun's galactic journey, all these motions exist in a state of exquisite balance. The forces at play, gravity, centrifugal effects, angular momentum, interact with mathematical precision to create a world where motion and stillness become indistinguishable. This isn't accident or coincidence. It's the natural result of physical laws working exactly as they must. Consider the delicate balance between gravity and centrifugal force at Earth's surface. At the equator, where rotational speed is highest, the outward centrifugal acceleration is about 0.0337 meters per second squared. Gravity's acceleration is 9.8 meters per second squared. The ratio is approximately 1 to 290. This means that roughly 99.7% of gravity's pull remains to hold us down, while only 0.3% is counteracted by rotation. But what if this balance were different? What if Earth rotated much faster? Let's calculate what would happen. For the centrifugal force at the equator to equal gravity's pull, Earth would need to rotate fast enough that the centrifugal acceleration reached 9.8 meters per second squared. Using the formula for centrifugal acceleration, which is the square of the velocity divided by the radius, we can calculate that Earth would need to rotate at about 7.9 kilometers per second at the equator, or about 28,440 kilometers per hour. That's about 17 times faster than Earth's current rotational speed. If Earth spun that fast, people standing at the equator would be weightless. They'd float. Buildings wouldn't stay anchored. The oceans would be flung into space. At that rotation rate, Earth's day would last about 1 hour and 24 minutes. The planet would likely tear itself apart, unable to hold its shape against such powerful centrifugal forces. The equatorial bulge would become so extreme that Earth would flatten into a disc-like shape, and eventually material would be ejected from the equator into orbit. This thought experiment shows us that Earth's rotation rate isn't arbitrary. It falls within a range that allows the planet to maintain structural integrity while still rotating fast enough to create moderate day-night cycles and weather patterns. Planets that rotate too slowly, like Venus, develop extreme temperature differences between day and night sides. Planets that rotate too fast, like Jupiter, develop extreme weather systems and pronounced oblateness. Earth sits in a comfortable middle range. The same is true for Earth's orbital speed around the Sun. Our planet moves at about 29.8 kilometers per second in its orbit. This velocity is precisely what's needed to maintain a stable, nearly circular orbit at our distance from the Sun, about 150 million kilometers. If Earth were moving faster, say 35 kilometers per second, we'd be on an elliptical orbit that would carry us farther from the Sun, cooling the planet during part of the year. If we were moving slower, say 25 kilometers per second, we'd spiral inward toward the Sun, heating the planet. The relationship between orbital speed, distance, and the Sun's mass is governed by Kepler's laws of planetary motion and Newton's law of universal gravitation. At our distance from the Sun, there's only one speed that produces a stable circular orbit, and that's the speed we have. Earth isn't choosing to move at this velocity. It's following the mathematical necessity imposed by gravity and orbital mechanics. The orbit is stable because the velocity is correct for the distance. This stability extends to the entire solar system. Each planet orbits at the precise speed required for its distance from the Sun. Mercury races around its tight orbit at 47 kilometers per second. Venus moves at 35 kilometers per second. Mars ambles along at 24 kilometers per second. The gas giants, much farther from the Sun, move even more slowly. Neptune, at the outer edge of the planetary system, orbits at a leisurely 5.4 kilometers per second. Each planet has settled into an orbit dictated by the balance between its velocity and the Sun's gravitational pull. These orbits have been stable for billions of years. The planets have completed countless revolutions around the Sun without flying off into interstellar space or spiraling into the Sun. This stability is a consequence of conservation of angular momentum. Once an orbit is established, it persists unless disturbed by an external force. The solar system, formed from a rotating disk of gas and dust 4.5 billion years ago, inherited its angular momentum from that primordial disk. The planets continue to circle the Sun along paths carved out when the solar system was young. But stability doesn't mean unchanging. We've mentioned that tidal interactions are slowly changing Earth's rotation rate and the Moon's orbital distance. Similarly, gravitational interactions between planets cause their orbits to shift very gradually over millions of years. These shifts are tiny, but over geological timescales, they accumulate. Jupiter's orbit, for example, likely migrated inward and then outward during the solar system's early history, a process called planetary migration. These migrations may have ejected planets from the solar system or caused others to crash into the Sun. The current configuration of the solar system is the survivor of billions of years of gravitational interactions. Planets that had unstable orbits were eliminated long ago. What remains is a system where orbits are spaced in a way that minimizes gravitational disruptions. The planets don't pass too close to each other. Their orbits don't intersect, except for Pluto and Neptune, and even they're protected by orbital resonances that prevent collisions. The solar system has settled into a stable configuration through a process sometimes called orbital natural selection. Earth is part of this stable system, and that stability is crucial for life. If Earth's orbit varied wildly, swinging from very close to the Sun to very far away, temperatures would fluctuate drastically. Life, which requires relatively stable conditions to evolve and thrive, would struggle or be impossible. The fact that Earth's orbit is nearly circular and hasn't changed significantly in billions of years created the stable climate backdrop against which life could develop. Similarly, Earth's rotation provides a rhythm that life has adapted to. The 24-hour day-night cycle governs the behavior of nearly every organism on the planet. Plants photosynthesize during the day and respire at night. Animals have evolved circadian rhythms, internal biological clocks that match the day-night cycle. Humans feel sleepy at night and alert during the day because our biology is tuned to Earth's rotation. If the length of the day suddenly changed, these biological rhythms would be thrown into chaos. This raises an interesting question about life on other planets. If we ever discover life elsewhere in the universe, will it have evolved on worlds with similar rotation rates to Earth? Or can life adapt to wildly different day lengths? We don't know yet, but it's a fascinating area of speculation in astrobiology. A planet with a day lasting weeks might develop very different life forms than a planet with a day lasting hours. The rotation rate of a world influences its climate, weather patterns, and the distribution of solar energy, all factors that shape the evolution of life. Let's also appreciate the engineering marvels that humans have built while accounting for Earth's rotation. When constructing very tall buildings, engineers must account for the fact that the top of the building is moving slightly faster than the base due to being farther from Earth's axis of rotation. For a building 1 kilometer tall, this difference in velocity is only about 7 centimeters per hour, utterly negligible. But for ultra-precise construction, every detail matters. When laying long railway tracks, engineers historically had to account for the Coriolis effect on moving trains. A train traveling north or south at high speed experiences a tiny sideways force due to the Coriolis effect, causing slightly more wear on one rail than the other. In practice, this effect is so small that other factors like curves in the track and uneven loading dominate. But in principle, Earth's rotation does create asymmetric wear patterns. The longest railway in the world, the Trans-Siberian Railway, stretches over 9,000 kilometers across Russia. A train traveling the full length at 100 kilometers per hour would experience Coriolis deflections on the order of several meters over the course of the journey if traveling on perfectly straight tracks. In reality, the tracks curve and wind, and the train's speed varies, so the Coriolis effect is masked by these larger factors. But it's there, a subtle reminder that we live on a rotating world. Particle accelerators, like the Large Hadron Collider, must also account for Earth's rotation. The LHC is a circular tunnel, 27 kilometers in circumference, buried beneath the border of France and Switzerland. Protons circulating in this tunnel at near light speed complete about 11,000 laps per second. Over the course of each lap, Earth rotates by a tiny amount, changing the tunnel's orientation in space. This effect is so minuscule that it has negligible impact on the experiments. But in principle, Earth's rotation does slightly affect the precise timing of particle collisions. These examples illustrate that Earth's rotation, while imperceptible to our senses, has measurable effects on sensitive instruments and large-scale constructions. The fact that we've learned to measure and account for these effects is a testament to human ingenuity and the power of scientific understanding. We've gone from being entirely unaware of Earth's rotation to incorporating it into the most precise technologies ever created. Now let's talk about what all this means for our understanding of motion and reality. The ancient Greek philosopher Aristotle believed that the natural state of objects was rest. He thought that objects moved only when forces acted on them, and that they would naturally come to rest when those forces ceased. This seems intuitive. When you slide a book across a table, it slows down and stops. Aristotle interpreted this as the book returning to its natural state of rest. But Aristotle was wrong, and it took nearly 2,000 years for humanity to realize it. Galileo Galilei, in the early 17th century, understood that the book stops because of friction, not because rest is its natural state. If you could eliminate friction, the book would slide forever at constant velocity. Galileo recognized that an object in motion tends to stay in motion unless acted upon by a force. This insight was codified by Isaac Newton as the first law of motion, also called the law of inertia. The law of inertia tells us that there's no fundamental difference between being at rest and moving at constant velocity. Both are inertial states. An object at rest will remain at rest, and an object in motion will remain in motion at constant velocity unless a net force acts on it. This means that constant velocity is indistinguishable from rest in terms of the physics governing the object. There's no experiment you can do inside a closed system moving at constant velocity that will tell you you're moving. This principle, sometimes called Galilean relativity, was later extended by Einstein into special relativity, which applies at very high speeds approaching light speed. But the core insight remains the same. Uniform motion is relative and undetectable from within. This is why we don't feel Earth's rotation or any of its other motions. We're in an inertial reference frame, or close enough to one that the deviations are imperceptible, moving smoothly through space. From our perspective, we're at rest, and the universe moves around us. This relativity of motion is one of the deepest principles in physics. It tells us that there's no privileged reference frame, no absolute standard of rest against which all motion should be measured. You can choose any reference frame you like, your own, Earth's, the Sun's, the galactic centers, and the laws of physics work the same way in all of them. This symmetry, this democratic equality of reference frames, is a fundamental feature of the universe. Einstein's general relativity extends this principle even further. General relativity tells us that gravity isn't really a force in the traditional sense. It's the curvature of space-time caused by mass and energy. Objects moving under gravity alone are actually traveling in straight lines through curved space-time. This is why we don't feel Earth's orbital motion around the Sun. We're not being pulled by a force. We're following the natural curvature of space-time created by the Sun's mass. From our perspective, we're moving in a straight line, and the universe curves around us. This is a profound shift in perspective. For millennia, humans thought of Earth as the unmoving center, with the heavens revolving around us. Copernicus moved the center to the Sun, but still imagined a fixed center and moving planets. Kepler and Newton showed that planets move along paths dictated by gravity and inertia, but still thought of space as an absolute stage. Einstein revealed that space and time are flexible, curved by mass and energy, and that motion is entirely relative. There is no center. There is no absolute motion. There's only the relative motion between objects and the curvature of space-time that guides their paths. From this modern perspective, The question, why don't we feel Earth's rotation, has a beautiful answer. Because motion itself is relative and undetectable. We don't feel motion. We feel acceleration, changes in motion. And the accelerations we experience due to Earth's rotation, its orbit, and its galactic motion are either too small to perceive or shared equally by everything around us, making them invisible. We are, in a very real sense, always at rest in our own reference frame,